right, I'm just going to have to mark the rest of the people absent. We can't wait. So, all right, hope we're doing okay. It's Wednesday, so you guys have your homework 4 is due by Monday, okay? And I noticed that a couple of you have already turned it in. Thank you. That's awesome. All right. The fundamental theorem of line integrals, the way that we do number 8, we're actually going over that today. So I didn't go in and look at what you did, but it's just, we're just going to evaluate those line integrals. So I saw a couple of you already turned it in. Okay. So all the rest of you, I need it by 5:30 on Monday the 23rd. We're going to finish everything out tonight. So you could actually, you can, if you don't want to have it hovering over you over the weekend, just turn it in before the weekend. Just turn it in early. Okay? So, whatever. So, there's some of you are just waiting until 5:29 on the day it's due. So, if you want to do that, if that's just be careful. All right, just be careful because I have to have it by 5:30 on Monday. It's the last homework assignment, and then we're going to have our final test and our final exam. All right. Okay, let's see. I want to be careful because I've been just people that aren't here at the beginning. I've just been marking them absent. So I'm not able to go back in and change all that. Okay, so I'm just going to mark people absent, and there's 6 people. I'll mark those 6 absent. I don't know what else to do. Okay, so let's go ahead and get started. We're going to do screen share. And we're going to review what we are doing with line integrals. We're going to review line integrals, okay? And then we're going to get into the fundamental theorem of line integrals and then Green's theorem, okay? I have a lot of examples with that to do for today. If we have time at the very, very end, if we have time, we can do another, the change the variables, but I'm going to doubt that we're going to have time for another one. We did a few of them last time anyways, okay? So so Monday, class on Monday, all right, we're going to spend the first maybe half hour going over the divergence theorem, okay, and then we're going to spend at least an hour reviewing for your test, okay. So Monday's going to be a big day. We're going to do a review kind of together. Your test is going to be Monday the 30th, okay, because we have Thanksgiving in there. So Monday the 30th, and your test is going to have some, there's a couple of problems. They're going to be big, long problems. Look at what we've been doing. The applications are kind of involved. So the lowest quiz grade will be dropped. Now, the lowest private question, so it says, has the lowest quiz grade been dropped? I usually don't drop the lowest quiz grade until after the test 3, right? So here's the deal. So if your lowest quiz grade, all right, if your lowest quiz grade is lower than your class average, I'm going to drop it and move it out of the way because it's bringing you down, right? But for some of you, if your lowest quiz grade is higher than your class average, I'm going to leave it in there because it's bringing your grade up. You know what I mean? Which means you're going to end up with 1,050 points. So, I'll drop your lowest quiz grade if you insist on me dropping it. But if your lowest quiz grade is higher, if your lowest quiz grade's higher than your class average, I probably should leave it there, right? Okay? I usually do whatever is beneficial to your grade, whichever way gives you the higher grade. Okay? So there's a couple of you that missed the quiz. You flat out missed it, so you got a 0. So those zeros I got to move out of the way. Okay, I just have blank boxes in Canvas defaulting to 0. So that's why after I finish grades out, any box that's left blank goes to 0. So I have to actually physically go in and move the 0 out of the way if you missed a quiz, okay? And if your lowest quiz grade is low, so if you don't mind, I'm going to wait until after Monday the 30th, okay? I'll wait because your final exam is not until December, so after your 30th test and before you guys do the final review, I'll have that lowest quiz grade out of your way if it's bringing you down. All right, so just let me know if that's going to bug you, but that usually works out pretty well. Okay, all right, I was answering a private question. So let's go ahead and get started with today's stuff. All right, so let's get started with today. Let me do the screen share, make this thing go. All right, it's loading. So, okay, so we're here, and here's the page. So something for you to write down, but I did add, see the red box at the bottom? That's the piece that I knew we wouldn't get to last time. I added that on to finish off line integrals, okay? So we started line integrals last time. We only got to the DS. We only got to the arc length portion. So this first blue box we got, and we've done examples of. We didn't get to the other ones, and we need to do the vector field also, okay? So if you took your notes last time, you want to add this last formula to this. There's 4 things with line integrals. We went over 3 of them last time, knowing that I wouldn't get to this one at all, right? So we need to finish up line integrals today. We're going to do 4 examples, all right? Or maybe 3 or 4 examples, whatever I have in here. Okay, then 16.3, we're going to go over the fundamental theorem of line integrals. 16.4, we'll go over Green's theorem. That's the plan for today. Move the chat bar over here. All right, so just quick overview. I'm going to come back to this page but so you can see what we're doing. We're going to do 1, 2, 3 examples of line integrals. Then we're going to move into the fundamental theorem of line integrals, which this is what it's all about. We're going to do 1, 2, 3, 4 examples, 5 examples of the fundamental theorem of line integrals. Then we'll get into Green's theorem, and we're going to do those 4 problems from the book, which I have all written out here. We're just going to do the problems in the book, those even problems, okay? So that's the plan. Hopefully we'll get through all of it, hopefully. Okay, if we don't, we'll have to finish it up Monday. The homework that you have to do for Monday, okay? So the homework that you have to do for Monday is... it goes up to the fundamental theorem. It does not include Green's theorem because I didn't know if I would get through all of it tonight or not. Okay, hopefully we will though. Okay, all right. So let me back up. Where are we? Get to the beginning. So that's what the plan is tonight. All right. So I have it all spread out, all those problems that we're going to try to do together. All right. So we did this last week. Last Monday. So line integrals, they're single integrals. Well, it's multivariate with single integrals, and you can't integrate one. You can't have one integral with 2 variables. You can't. Okay. So if you have one integral in 2 variables, you have to fix it so it's only one variable. How do you take x's and y's and fix it so it's only one variable? You're going to have to parameterize it, right? You're going to have to parameterize it, and we learned how to, you know, when it's over like a line in 3 space, right? A line in 3 space, okay, or even in 2 space, whatever you're doing. Then when you parameterize it, we did that back in chapter 12. You're going to need to find the parallel vector and take a point and write your parametric form of where you're traveling along, and take that parametric form and substitute it in. Okay, so we did a few of those examples last time, and what I have in here for today, if all goes well here, we'll do 3 more examples of this today. We've got 3 more for today. Okay, so we'll do one of these with the arc length, we'll do one of these with the differential, and then we'll do a vector field. Okay, and we graphed a vector field last time also. Okay, so this is from last time. All right, so screenshot or whatever in case you've lost your notes from last time, because I'm not going to take the time to have you write every single thing down. Just we got the vector field to do, dot product, that's a dot product. All right, so if it's a vector field along a curve, you're just going to take the vector field, you're going to evaluate the vector field as a function, and you're going to dot product it with the function. I'll just show you that through an example. All right, so let's do this one. My page isn't turning. All right, hang on. Got to get the page to turn. There we go. Okay, so here we go. So let's do this one. So this is your textbook. We already did a couple of these problems. So this is your textbook, and it's number 11. All right. Most of the problems, the majority that we do, are going to be even numbered problems, but we're going to do this one. Okay. So this is x, y, and z. You have one integral with 3 variables. We can't do that, right? We can't do that, okay? So what do we have to do? We can't have one integral with 3 variables. So what we need to do is we need to parameterize this, right? We have to write this one integral all in terms of t, and this is along a curve, okay? So you have to include the arc length parameter on this one, okay? So how do we figure out what the curve is, what we're going to travel along, okay? How do we figure out how to parameterize this? You're going to take your 2 points here. All right, we want to write our parallel vector. Okay, so what we want to do with these 2 points is we want to write the equation of the line through these 2 points, right? So the equation of a line through 2 points, okay, so what do we have to do to get the equation of a line? And these are ordered triples, right? So we're going to use parametric form. So we're going to do the x's, so 1 minus 0, 2 minus 0, 3 minus 0. I suppose I don't have to kind of show the work here. So your vector is actually 1, 2, and 3, since it's already in the right form, okay? So there's your parallel vector, and then you can take whatever point you want. How about using 0, 0, 0, right? Okay, and so so x equals, right? X equals your point plus 1 times t, okay? So y equals your point value 0 for the y coordinate plus 2 times t. So z equals 0 plus 3 times t, okay? So x is t, all right? Y is 2t, z is 3t. I didn't have to write all those pieces out, all right? Do you see it? Okay? So here's your parametric form of your line. This is parametric form. This is parametric form. Of the line through those 2 points. All right, so that's what we're doing. And so you're going to take this parametric form. We're going to take the x's and the y's and the z's and substitute it with t, 2t, and 3t. Okay? So let's do that and set it up. So you're going to have, we'll get the bounds in a moment, but x is t, and then you have e to the y is 2t, and z is 3t. Okay? Now, we need the arc length component, so you're going to have to multiply. So square root of 1 squared, okay, plus the square root of 2t, so that's going to be square root, I'm sorry, take the derivative dx dt, so that's going to be 1 squared dy dt, take that derivative and square it, and then take the derivative of the z and square it, okay, dt. So there's the integral there in blue, all right? So all we have really left to do is get our bounds. Okay, so we need to get our bounds. All right, so let me change up the color a little bit. Okay, so now the bounds. Bounds need to be in terms of t. So what do you want to use, x or y or z? Okay, x or it doesn't matter which one you use. Well, x is t. That's easy enough, right? Since x equals t, all right, x equals t, all right, and you can use your point from 0, 0, 0, right, to 1, 2, 3. Okay, so over here, so since we're using the x, it doesn't matter which one you use, right? So use the x, okay, well, since x goes from 0 to 1, t is also going to go from 0 to 1, all right? So t is going to go from 0 to 1, all right? So the bounds are 0 to 1. So there's your integrand, all right? Now we can integrate this, right? Can't have 2 variables, can't have 3 variables, okay, 1 variable. All right, we can't have 2, can't have 3, all right, and we integrate this, all right, so let's go ahead and do the integration. So what is that number under the radical? 9 plus 4 plus 1, that's radical 14, I'll pull that out front. So we have the square root of 14, we're going to integrate from 0 to 1, t e to the 6t squared. Okay, how do we integrate this? Well, let's let u equal the exponent, just u sub, right? So du is going to be 12t. So du over 12t. And then rewrite the integral. So you have radical 14. And so we're going to integrate t e to the u, and then dt is du over 12t. So the t's cancel. So we have radical 14 over 12 out here, and the t's cancel. So there's your integral of e to the u. So when you integrate e to the u, you just get e to the u. So radical 14 over 12, e to the, what is u? 6t squared. And we want to evaluate this from 0 to 1. Okay? So radical 14 over 12, plug in the upper bound, you get e to the 6th power. Plug in the lower bound, plug in 0, anything to the 0 power is 1. And that's about it. We can't go any farther than that. Okay? So you can't integrate one single integral with multiple variables, right? So what do we need to do? We need to parameterize it. This is how you parameterize it. All right, ds means it's along. You got to include the arc length component. So we did examples just like this last time. I think we did number 10 and 12 or something. So, there's this one. Okay. So x's and y's and z's, change them to t's. How? Take those 2 points and write parametric form of your equation of a line and substitute it in. That's what we do. Get your t-bounds. And that's it. Okay, we'll do the next example. We're going to do 3 of these examples. This is reviewing where we left off last time. So just reviewing where we left off. So you have to do this on your homework. There's only 8 problems on that homework that you need to do. So 8 problems total for Monday. Please make sure you do all 8 of them. Okay, so 8 problems, 25-point assignments. So I guess they would be worth 3 points each, right? 8 times 3 is kind of 25-ish, 24 plus a point left over for your whatever. All right, moving forward. Okay, just holler if I'm going too fast or anything. I want to try to pace us so we can get through this tonight. So we kind of sort of have to kind of finish out the course as best we can tonight, don't we? Monday's review, following Monday's your test, following one is review for the final, and then the final. We got to try to finish up. All right. Next problem, next page. Okay, my screen is frozen. I have to unfreeze my screen. Next page, here it is. Next page. All right. So we have a single integral with, now this has dx, dy, dz. So I'm going to show you all 3 of them at once, right? I'll show you what to do with all 3 of these at once. All right, but what do we have to do first? X's and Y's and Z's. You can't integrate single integral with 3 variables. Can't do that. So we need to parameterize. Okay, so we need to parameterize. So you get the hang of this. Okay, so we have 2 points in 3 space. Okay, and so we need to write the equation of the line. And write in the equation of a line. Remember, we have 3 ways to write the equation of a line. We have symmetric form, vector form, and parametric form. Parametric form is where we save ourselves here. Okay, parametric form. So let's take these 2 points and write the equation of the line parametric form. So we need our parallel vector. All right, so I'll set it up for you. So 4 minus 1, 1 minus 0, 2 minus 0. So your parallel vector is going to be 3, 1, 2. There's the parallel vector we need. Okay, and then because I did sub 2 minus sub 1, 1, 0, 0 will be my point. So write the equation. So x equals, it's going to be 1 plus 3t. Okay, so you take the x sub naught plus a times t. Y is going to be y sub naught plus b times t. So y is going to equal t. And then z is going to be 0 plus 2 times t. So here's my parametric form right there. There's my, that's what I have to do over here. All right. So now, what do I do with dx and dy and dz? Well, dx is come here, just take the derivative of the x, it's 3. dy is the derivative of the y, 1. And then dz would be the derivative of z with respect to t. Okay, so it would be 2. So this is how you handle, you don't have to worry about the arc length parameter here. You're just going to take the differential. You're going to differentiate the x, the y, the z with respect to t. That's how you handle these. All right, so let's write our integrand and then we'll go get the bounds. All right, so we write our integrand and then we'll go get the bounds. So the integrand, we'll get the bounds in a moment. Z squared, so that's 2t. Okay, all right, so that's 2t and we want to square the 2t. So it's the z squared, and then derivative of the x, that's 3, okay? Plus x squared, 1 plus 3t quantity squared times the derivative of the y would be 1, and then y squared is going to be t squared times derivative of the z would be 2, and all this is dt. There's your integrand. All right. So we're going from 1, 0, 0 to 4, 1, 2. Okay. Do I use X, Y, or Z to get the bounds? I know what I want to use. I want to use Y. Y and T are the same thing. I want to just use, so since Y equals T, right? It doesn't matter which of these parametric curves you use, right? But I think I want to just use Y because I don't have to do anything. Okay, so Y is 0. Okay, so substitute 0 in for Y. Substitute 1 in for Y here. So the bounds go from 0 to 1 again. That's just like coincidence that the last couple of examples we did, the bounds just go from 0 to 1. All right? I'm doing your textbook problems, so the bounds seem to be, but that's how you figure it out. It doesn't matter if you go to the X, the Y, or the Z. The bounds are going from 0 to 1. Okay? All right, and then evaluate this. Okay, so what do you get when you evaluate this? Let's go ahead and simplify this a little bit. So we're going to integrate from 0 to 1. 3, so 2 squared, that's 4 times, so that's 12t squared. Okay, plus, FOIL this, so you get 1 plus 6t plus 9t squared. And then this is 2t squared, isn't it? Okay, dt. Combine like terms. So 0 to 1 is the integral. How many t squareds do I have at 12, 13, 14, and 9 is 23. 23 t squareds. Okay, 23 t squareds plus 6t plus 1. Okay, so this is what we're integrating. This isn't too bad. This is number 15 in your book. Hopefully you've already done it. Hopefully you sit down and practice some of these between Monday and today. But so 23 t cubed over 3 plus 6 t squared over 2 plus t from 0 to 1. All right, plug in the upper bound, so 23 thirds. Plug in the upper bound, so you have 6 halves, which is 3 plus 1. Plug in the lower bound, you get 0. All right, so 23 thirds plus 12 thirds, I guess. So it's 35 thirds. I mean, we're going through and doing the integration like we did back in Calculus 1. Of course, obviously, the really super important thing is you guys understand the process to set it up, okay? And the concept of you can't evaluate a single integral with more than one variable, all right? So if you have a single integral, you're only allowed one variable, all right? You have more than one variable, then your option is that one of them's got to be a constant, okay? But if you have more than one variable and they're all variables, then you're going to have to parameterize. You got to get it in terms of one variable. Yeah, getting the hang of it? Questions? I have the chat bar up here. You guys are real quiet there. Okay. So I've got one more example because we need to do an example with that vector field. So if it's a vector field, we'll just write the vector field in terms of t. I'll show you an example of how that works, okay? So we're going to do, I think it's number 20 in your book. We're going to do that one next with the vector field. All right, so I'm going to go and turn the page. Your page isn't turning, so I need to undo this. Okay. Yes, so number 20 in your book, and then we'll move on to the fundamental theorem of line integrals. Okay, so this is number 20. It gives you the vector field, and it gives you a vector. Vector field. Okay, remember we graphed that? Remember we graphed a vector field on Monday? Okay, so we graphed a vector field. Yeah, so vector field. So what do we want to do? We want to, let me write the formula down. So we have this, right? This is what the directions want us to do. Okay, so how do we do this? Well, it's going to be, we're going to integrate A to B, okay? See if I can write this neat enough. So how do we do that? All right, this is what your formula says. So how do we do this? Well, I'll show you. Okay, so first of all, we need this. Okay, so how do we get this? Well, in your R of t up here, okay, I'm going to write up here. Okay, so R of t, this is your t squared is your x, t cubed is your y, negative 2t is your z. Those are those pieces. Okay, what color can I use to do that? Okay, let me see if this is going to work. Okay, so that's your x. Okay, that's x. All right, this over here, t cubed is y, isn't it? All right, and then z is negative 2t. Okay, so we want to evaluate. This is what this means, right? This is what this means. Okay, because we want to evaluate the line integral, so we have to write it in terms of t. So you want to take your vector field and you're going to merge in your position vector to that vector field. Okay, and so we need to write it as a function of t. Okay, so you're going to change it. Look at these. All the x's in here get changed to t squared. All the y's in here get changed to t cubed. All the z's in here get changed to negative 2t. Okay, so what is our vector field? This vector field, what is it? I'll write it with this notation. Okay, it's going to be x. What is x? T squared. Okay, plus y squared, which is t cubed squared. Okay, your j component is x times z. Well, x is t squared, z is negative 2t. And your k component is y plus z. Well, y is t cubed, all right, plus z is in negative 2t. There's that vector, okay? So I suppose I can simplify it a little bit. So what do I have here? I have t cubed plus t to the 6th. I have negative 2t cubed here, and I have t cubed minus 2t. So this is going to be that piece. I'm going to do a dot product. There's that piece, okay? Any questions on how we got that? All right, now what do I need to dot it with? Okay, so this is how you would take remember we got to write the integral in terms of t, okay? So you're going to take your vector field. How do you write that in terms of t? Well, you're going to take your, they give you these, right? This is number 20 of the book. So you're going to write this in terms of t squared in the first part, t squared plus t to the 6th. Oh yeah. Thank you. Yay. I copied this wrong, so t squared. Yeah, t squared plus t to the 6th for the first part. Good. Thank you. All right. Okay, and so we want to dot it with, now this is more straightforward, right? You know what this is, right? So what are we doing here? We're going to take the position vector they give us, we want to differentiate it. Okay, so let's go ahead and do that. So the other piece that we need is we need the derivative. We need the derivative of our position vector. Okay, so let's get the derivative of the position vector. And what's that going to be? Let's see, that's going to be, what can I write? I'm going to write it in this notation if you don't mind. So 2t, 3t squared, and negative 2. Okay, so we're here. All right, and so what do we have to do now? All right, so we're going to integrate this. Now they gave us the bounds, didn't they? Okay, so they give it for these, they're going to have to give you the bounds, all right? So let's set up our integrals. Integrate from 0 to 2, all right? We want to take this vector, so here, I'll write it out. So we want to take this vector, t squared plus t to the 6th, negative 2t cubed, and then t cubed minus 2t, right? We want to take this vector and dot it with this one, 2t, 3t squared, negative 2. Okay, so we're going to dot those. So we end up with let me simplify this. So it's going to be, remember, dot product, so it's this times this. All these things coming back from chapter 12, right? So this times this. Okay, so let's do the dot product. So you're going to have 2t times t squared plus t to the 6th, okay, plus this times this. Okay, so it's negative 2t cubed times 3t squared plus that times that. So it's going to be t cubed minus 2t times negative 2. Remember dot product? So this times this plus this times this plus this times this, dot product. Okay, so dot product, we had right the equation of a line, all these treasures coming back from chapter 12, right? So simplify, and so what do we have? 2t cubed plus 2t to the 7th. That'll be a negative term, minus 6t to the 5th, and then minus 2t cubed plus 4t. So we got this going on. All right, what else? What do we see here? You kind of see that the t cubes cancel. All right, can I do that? Could I slow down a bit? Sorry. Yeah, I'll slow down a bit. So, yeah, so this is just these are the later problems there, right? So the object, right? The moral of every single thing we're doing here is you're evaluating a single integral, and the problem is that you have you have x's and y's and z's going on, and you have one integral. Okay, so these are all the different techniques of how you would take the one integral and parameterize it, change everything in terms of t, or when you're dealing with a vector field, then it's showing you that you're going to, because it's a vector field, right? Vector field, so you can take the position vector components and merge them into your vector field. The whole object, though, or these are all the different methods proven to be true. Recently also, like within the last 100-ish years, right? 100, 150 years. Well, I mean, that's recent for math world, you know, when some of our topics go on thousands of years, right? And we're trying to write everything in terms of one variable. So, and I'm trying to give you some really nice, well-rounded variety of examples. So you'll have a nice little notebook of examples for yourselves, okay? So, and this is number 20 from the book, and so when you practice the odds. All right, so that's what we're doing. So this is what you're going to do here. So when it's a vector field involved, then we're going to use the position vector to break the vector field down to component just in terms of t, each component in terms of t, okay? And then we're going to do the dot product, which we're going to need to see. We need to see this because this is going to carry over to the fundamental theorem of line integrals, and it's going to carry over to Green's theorem. All right, so I'm going to keep going now, so I hope that's okay. So the 2t cubes cancel, so I have 2t to the 7th minus 6t to the 5th and 4t. So we want to integrate this, okay, and I want to really badly contain this to this page. Hopefully I can get it to this page, okay. Do the integration, you get 2t to the 8th over 8, so that's going to be t to the 8th, right, over 4 when you simplify it, okay. Minus 6t to the 6th over 6. Okay, so the 6's cancel, so t to the 6th. Okay, and then 4t squared over 2 plus 2t squared. We want to evaluate this from 0 to 2.
You're not writing, Professor.
Oh, okay, that's because I stopped for a moment. sorry, so I went ahead, so the 2t cubes cancel, and it freezes up when I stop. So the 2t cubes cancel, so I just rewrote it, right? So we have 2t to the 7th minus 6t to the 5th, and then plus 4t. That's what we have to integrate because the t cubes cancel. Integrate 2t to the 7th, you get 2t to the 8th over 8, 2 over 8, so it's t to the 8th over 4, okay? Integrate 6t to the 5th, that's going to be 6t to the 6th over 6, so t to the 6th, okay? Integrate 4t, and you get 4t squared over 2, and so 2t squared, okay? So that gave me a little bit of an opportunity to kind of check over my answer also, okay? And then we're going to evaluate. That lower bound is 0, that upper bound is 2, okay? So we're going to plug in the upper bound. When you plug in the upper bound, you get 2 to the 8th power. So actually take out a 2 to the 2nd in the denominator divided by 4. So you really just want 2 to the 6th power. 2 to the 6th power is 64. So we have 64 minus 2 to the 6th power. Oh, that's 64. Okay. Plus 2 times 2 squared. So 2 times 4 is 8. Plug in the lower bound, you get 0. So answer is 8. Okay, so that's your answer, all right, but that's, all right, and this is the last example we're doing. We're going to move on to the fundamental theorem of line integrals, but the object is, with this section, okay, 16.2, you have a single integral, you can't have x's, y's, and z's to integrate, right? You can only have one variable, so you've just got to figure out how you're going to break it down to one variable, and the most common, which you're going to see everywhere, is the parameterization, all right? So just change everything to t and use the parameterization, okay? All right, unless this is a vector field, right? So a vector field, we can actually merge in the vector field component, the position vector, to break down the x's, y's, and z's, all right? Okay, good. So this example was contained to one page too. So whatever you do, some of you are writing it down with me and doing it with me, and that helps. Okay, so or if you're take a screenshot, whatever you need to do. So we're going to move on to 16.3 next. We're going to move on to the fundamental theorem line integrals. Okay, so we're going to move on to the fundamental theorem of line integrals. I think I want to try to do 5 examples of that. All right, and then I want to get Green's theorem. So we're going to try to do as much as we can to get through it. Okay, so Green's theorem. And ready? I'm going to turn the page. Of course, it's not going to turn because I'm talking and not writing, so. Okay. 16.3, the fundamental theorem of line integrals. Of course, you know, in the textbook, these things are explained over 6, 7, 8, 9, 10 pages, right? And what am I doing with that? I'm taking this 6, 7, 8, 9, 10 pages, and I'm condensing it down to three little boxes, okay? So I don't have proofs here for you. I don't, you know, because we need to finish the course. And I did a bunch of proofs at the beginning of the course, but so you need to read the book to see why these things work. I'm going to just show you what they are and how they work, right? For the rest of the course, it's what you're going to get. So I'll show you what they are and how they work. Okay, so why do they work? You want to read the book for that. You have a lot of really good examples in the book. All right, I choose not to do the examples in the book. I don't know if you know, I mean, the whole course, I choose not to do the examples in the book. Instead, I like to pull them from the events because you can read the book and you can read the examples. And so why am I going to do them again when you can just read them, okay? So some of you guys that don't have an answer key or anything, I'll do the evens, so you'll have, and this way you practice the odds, because that's what's on the syllabus, right? And then you practice the odds and check your answers in the back of the book. Just practice as much as you can, all right? Fundamental theorem of line integrals, which is going to lead us into Green's theorem. So first of all, there's 3 concepts here, okay? The first box is really a summary of conservative. The word conservative is what they use to describe a vector field, okay? A vector field, all right? So a vector field is conservative. So this is a vector field, okay? Just in terms of I and j, all right? So vector field in terms of I and j. and it's conservative. All right, vector field is conservative if the partial of the I component with respect to y and the partial of the j component with respect to x are equal to each other. Okay, and we need these phrases right here for Green's theorem. So then this is building up to the Green's theorem, actually. Okay, so if you have a vector field, okay, so you have a vector field. You see you have x's and y's with the I, x's and y's with the j. You have a vector field, right? Okay, so and so this is not like a vector value function, right? This is a vector field. So you got the x's and y's, sometimes z's with the i's and j's and k's, all right? So if you have a vector field, it's conservative if this is true, okay? Now, conservative is, so we're only going to use this. So if you have x's and y's and you're checking if it's conservative, we do this for x's and y's. If you have x, y, and z, which you won't in this section, unless they just tell you it's conservative, you won't in this section because you would actually need to compute the curl to determine if it's conservative or not. You'd compute the curl, which is, I'm going to show you that on Monday, okay? So our vector field, if our vector field is conservative, when the partial of the I component with respect to y and the partial of the j component with respect to x are equal. Okay, so if your vector field, if you have this true, so if your vector field is conservative, then you can take your vector field and we can write it as a function. But we can't always write it as a function. We can only write the vector field as a function. We can let a function represent the vector field if the vector field is conservative. So if the vector field is conservative, then we can take the vector field and we can write it as the function because that means the vector field is the gradient. Remember the word gradient? The vector field is, those are the partials, and we can integrate the partials to get the function. Okay, so fundamental theorem of line integrals. This is where, so we have a vector field. Okay, all right, and then once you take your vector field, write it as a function. Once you take your vector field and write it as a function, and you can actually use the fundamental theorem, plug in the b point minus plug in the a point, and you can compute it, just like the fundamental theorem of calculus. Okay, so what we need to do here is we need to take our vector field, we need to write it as a function, and then we're going to evaluate it, okay? But we can't always take a vector field and write it as a function. We can only write it as a function if this is true. If the partial of the I component with respect to y and the partial of the j component with respect to x are equal. If that's true, they called the word as conservative, okay? So if that's true, then you can take the vector field and we can write it as a function. So we can use, because we can use functions to evaluate. All right. I don't know if my words mean anything to you. You can read the book if you want the author's perspective, or you can just follow along. We're going to do 5 examples, I think. We're going to try to do 5 examples. I'm going to keep an eye on the clock and make sure we have time to start Green's theorem today. So, worst case scenario, we do 4 instead of 5. But I think once we get to the examples, and then I'll go back to this page, and so you can get a little summary of what we're doing. Okay. So, so we want to take a vector field and find the function that represents it. Okay? So hopefully you were able to scribble these down. These are, like I said, 16.3. I mean, my notes in here are like that big, all right? So, and I think I have videos on all of these things. I don't know if I have videos where I did a whole bunch of examples and explained all this stuff. So I don't know if you looked at those yet, but might send you an email and just send you all the links in case you want to check them out. Okay? So let's do some examples, and I'm talking over this, so where are the examples? Well, let's see. Oh, yay. Okay, so let's start with how many are we doing? We're going to do number 6, okay, and 10, and 12, 15, and 16. Yeah. So let's try to do 5. Let's see if we can do 5 so you feel really good with this topic, all right? So number 8 on homework, the homework you have to turn in Monday, number 8 is this, right? Okay, and I didn't put any Green's theorem on there because if we're going to get it started today, but I just wanted to make sure. But these 5 examples you should be good and comfortable getting through. So the directions, this is in the textbook, right? So chapter 16, section 3, it's problem number 6. Determine whether or not the vector field is conservative, okay? If it is conservative, find the function that represents the vector field. Okay, so we're going to find the function to represent the vector field. So let's go through this so you can see how it works. So we want to see if it's conservative. Remember how to check conservative? So to check conservative, let me use a small pen. So to check conservative, we want to take the partial of p with respect to y. Well, okay, so to check conservative, we want to take the partial of p with respect to y. And we want to see if it's equal to the partial of q with respect to x, okay? Do you remember, so this piece right here was the p, right? This piece right here was the q. Okay, so can you see it? So let's do that. Let's check it out and see. All right, so what is the partial of p with respect to y? E to the x. What's the partial of q with respect to x? E to the x. Okay, so yes, it's conservative. This vector field is conservative. So we are able to find a function to represent this vector field. Okay, so let's go and do that. Are my words, am I okay putting my explanations in here so you can see what we're doing? What if the partials, what if they weren't equal? If these were not equal, you would say this vector field is not conservative and you're done with the problem. So you determine whether it's conservative. Okay, so if the partial of p with respect to y, if the partial of so your I component with respect to y, your j component with respect to x, take the partials. If they're equal, we're going to find a function to represent this, okay? Because when you're using the fundamental theorem of line integrals, you got to use it on the function, not the vector field. So so we need it. So if these are not equal, you can't find a function. There's no proven way. It's not proven. There's no proven way to find a function. Okay, but they are equal. So we're going to find the function. All right. So we're going to find the function. So how do we find the function? Well, because it's conservative. Okay. So how are we going to find the function? So since this is conservative, all right, then
you're frozen.
Okay. Sorry. So since the vector field is conservative, all right, then your vector field is the gradient of the function. Okay. And that's proven to be true. You're going to have to just take, a morning with a pot of coffee and read through the proof. It's a really, all this, and Green's theorem proof and all that stuff. It's really good stuff, but you're going to have to read through that. Okay. So that means your vector field here, this is only I and j, right? So that means you partial with respect to x, partial with respect to y. So because the vector field is conservative, okay, that means that this piece right here, that is the partial with respect to x, And this is right here, it's the partial with respect to y. That's what it is, okay? Now, so we know those are the partials. What are we looking for? We want the function. We've got the derivatives, we want the function. So hopefully you can kind of see where we're going to go with this, okay? So what do we have to do? Well, so we're going to, so this means that the partial with respect to x, I'm going to write it over here, is y e to the x. That's what it is. The partial with respect to y up there is what? It's e to the x plus e to the y. Okay, all right. So how do we know this? Well, because we checked for conservative, okay? Because it's conservative, because we got the equal. So because it's conservative, by definition, that means the vector field is the gradient, okay? That means that the components are the partial derivative with respect to x, partial derivative with respect to y, okay? So we know the derivatives. What are we looking for? We're looking for the function. We want the function to represent this vector field. How do you find the function? Well, integrate the derivative to find the function. All right. Which component? Well, we're going to need to do both of them, but one at a time. Okay. So we're going to start by integrate the f. All right. So to get the function, we're going to integrate, what is these? So y e to the x, right? But we're integrating that with respect to x. When you integrate y e to the x with respect to x, what do we get? When we integrate y e to the x with respect to x, we get y e to the x plus a constant of integration, but it's not a constant of integration. We're going to call this g of y. Okay? You're not going to put like plus c, not yet. Okay? So you're not going to put plus c yet. So we're trying to get the function. We're on our way to getting the function. Okay? We're getting there, okay? So we went ahead and we integrated the x component. When you integrate the x, you get this, okay? Would it be, we're integrating with respect to x, so no, it wouldn't be that. It would just be y e to the x. Integrate e to the x, you get e to the x. So you integrate y times e to the x. Y comes down as a constant. It's just e to the x. Okay? So, yep. And so we're here. Okay? So now what do we have to do? Well, now we're going to take this, okay, because we got to merge in the y component, right? So we have to merge it. We're coming up with our function. We have the partial with respect to x, partial with respect to y. We know those are the partials. We got to build a function off that. So you're going to, first of all, you're going to integrate the f, integrate the x part, okay, integrate the x component with respect to x, okay. All right, but your constant of integration, you're not going to put plus c here. Your constant integration is going to be g of y because we got to do the y piece now. So what do we do next? We're going to take the partial with respect to y of this answer right here. I'm not writing, so let me go back, okay. So now we want to take this right here we're going to take the partial with respect to y. Take the partial with respect to y. When you take this partial with respect to y, you get e to the y, taking the partial of this with respect to y. So when you take the derivative with respect to y, you get e to the x. E to the x. Okay, you get e to the x. Plus, taking the derivative with respect to y, that's going to be the partial of g with respect to y. Okay, and then what we want to do is we want to substitute this in. Okay, so we want to take this, and we're going to take this, and we're going to substitute this right in here for y. Okay, all right, this is f of y, this is f of y, substitute. Substitute, so you have e to the x plus e to the y. I'm making a substitution equals e to the x plus, all right, all I did on the left-hand side was make a substitution. Kind of a lot of steps to this, that's why I want to do 5 examples, okay? All right, then what? Well, the e to the x cancels on both sides, so let's get those out of the way. It doesn't always cancel, but yeah, those e to the x's cancel, so we can subtract that from both sides. They go away. So when you subtract that out from both sides, you have e to the y on the left, and you have g y of y on the right. You have this, okay? Now what? Well, this is our partial with respect to y. Now we're going to integrate both sides, okay? Now we integrate. Let's integrate both sides with respect to y. Integrate both sides with respect to y, okay? So when you integrate the left side, integrate e to the y, you get e to the y plus a constant. Okay, K or C, whatever you feel like using. Your textbook uses K. The right-hand side, you're integrating the derivative. Integrate the derivative and you get the function. Okay, so that's what your g of y is. And so this is the substitution. This is the substitution that we're going to make right in here. Okay, so we're going to take this and we're going to substitute this into here. So we're going to so what do we have for our partial x is ln y plus y over x. The partial with respect to y is ln x plus x over y. Okay, so we have the partials. What do we want to do? We want to find the function. All right, what do we want to do? We want to find the function. So I'm going to start with the x and then do the y. Okay, I don't think it matters. I've always started with the x and then did the y. It probably doesn't matter which one you start with. So to get the function, it should make sense that you're going to integrate the derivative to get the function. And which derivative do you integrate? One at a time, because you can only integrate with respect to one variable at a time. So partial with respect, so you're going to integrate ln y plus y over x. We're going to integrate this with respect to x. Okay, so integrate with respect to x. What do you get when you integrate this with respect to x? You're going to have x ln y for the first term. Okay, and then when you integrate y over x, what do we get? We get y times ln x, don't we? Plus your constant, but we still have the other. We still have the y to go, so we don't have a constant yet. We have a function, potentially g of y, and we don't know what it is. Okay, so. All right, so far, this is what we got. So far, here is our function. Our function is at x ln y plus y ln x. Those are two pieces of my final answer, okay? I just have to see that when I integrate the y component, if I'm going to have any more to add on to this, okay? So far, my function that represents this vector field, there it is. There's a couple of pieces of it, okay? What do I need to do next? Okay, so next, I need to take the partial with respect to y. All right, so I'm going to take this answer right here, and I'm going to take the partial of this with respect to y, so I can compare my next one. All right. So what is the partial with respect to y? So it's going to be x times derivative of ln y. So it's x over y. And what's the partial here with respect to y? It's ln x. And what's the partial here with respect to y? It's just the partial of g with respect to y. All right. So I'm taking what I circled here, and I'm taking the partial with respect to y. All right. What do I do next? Well, next I'm going to substitute in. All right. I'm going to take the partial of y. I'm going to take this and substitute that in here. Substitute it. Okay. So what do I have? I have ln x plus x over y on the left. I have x over y plus ln x plus my partial of g with respect to y. All right? Notice what happens here. Both the terms drop out. Okay? Everything drops out, so I have 0. That happens on a lot of your homework problems, and I don't know why the author did that. All right? So I have this, okay? Now, what do I need to do with this? I need to integrate, because I need to know what when I integrate the partial of g with respect to y, when I integrate it, I'm back to g of y, and this will tell me if I have any more pieces to add. So what I need to do now is I need to integrate with respect to y, integrate with respect to y, both sides with respect to y, okay? So what do I get when I integrate this? I get 0 times y plus a constant, because I got nothing on the left side. What do I get when I integrate the partial of g with respect to y? I have g of y. All right, and what am I going to do with this? I'm going to take this and I'm going to substitute it in right there. Okay, substitute it in. All right, so, and write my final answer. So my final answer is going to be, all right, so you can call it f of xy, or you can just f equals, okay? So my final answer, here it is. My final answer is x ln y plus y ln x plus whatever I came up with, which was nothing, just k. All right. Final answer is x ln y. All right. What is it? Plus y ln x. And then plus g of y, which is my k. That's your final answer here. Okay. And then I think the next examples, we'll get to examples where we're actually evaluating them. So taking a vector field and writing it as a function. Vector field as a function. That's the steps you go through. So you need to do the odd numbers in the book, right? 1 and 3 and 5 and 7 and 9. It's good problems in the book, pretty repetitive. I think one of those is going to be not conservative, can't find a vector field, but the rest, most of the other ones, you know, in this process here, to write a vector field, you just need to practice some problems. You just need to go through and practice some. All right. I mean, I've got one on your homework to do, and they don't take long. All right. These aren't the long ones, right? The long problems that you have to do, homework that's due by Monday. All right. So the long ones you have to do are like the center of mass, which isn't as bad as the one we did in class, and then your change of variables. Those tend to be a little bit longer problems. But this one's okay. Questions at all? Got the chat bar over here. The couple questions that came through are just private. So, all right, we have more examples. I have 5 of these. Okay, so let's see if we can try to finish the other 3, hopefully by 7 o'clock, so we can start Green's theorem. I have 5 of these. I don't know that we need 5. That might be overkill to do 5 of them, but all right, let's do, hopefully this next one will have bounds. All right, so let's do this one next. Yay, so we're actually going to use the fundamental theorem. Okay, so this is number 12, same section in the book. We're doing the evens around your odd numbered problems. The odd numbered problems are really good. Okay, find the function. All right, so they're already telling you it's conservative. Okay, so yeah, it's conservative. Okay, so if you have to find the function and they're telling you the vector field is equal to the gradient, then we're just going to go ahead and find the function. All right, and then part B, yeah, then we're going to evaluate it. Okay, so instead of having a constant of integration, we're going to evaluate it. Your answer is going to be a number. All right, so let's see how this works. Well, first of all, we have to find our function. All right, so how are we going to find our function? Well, we're going to take the partial with respect to x is going to be 3 plus 2xy squared, and the partial with respect to y is 2x squared y. Did I copy it right? 3 plus 2xy squared, 2x squared y. Okay, so they're telling you here, find the function. You don't have to check conservative now. They're telling you that it is conservative. Okay, if you take the partial of this with respect to y, we can do that if you want. You get 4xy, don't you? Okay, so partial with respect to y gives you 4xy. Partial with respect to y gives you 4xy. Okay, it's conservative, but they're telling us to just do it. So they're basically telling us it's conservative. We're not checking that. All right, so that means it's conservative. That means that your vector field, okay, is equal to the gradient, right? That means that you got the partials going on here. All right, I didn't write that very well. Okay, that means that, all right, that means, let me see if I can do this without messing it up. That means that this is the partial with respect to x. That means that this is your partial of the function that we have to find, right? Okay, so that's the partial with respect to x. That's the partial with respect to y. All right, so I wrote those down here, okay? So we want to find the function. So to find the function, you're going to integrate the derivative. This should make sense. You integrate the derivative to find the function. We can only integrate with respect to one variable at a time. So to find the function, let's integrate 3 plus 2xy squared with respect to x, which means y gets held constant, okay? All right, because we want the function that represents this vector field. Do the integration with respect to x, and you get 3x plus x squared y squared plus constant of integration, but we can't do that yet because we still have another variable involved to integrate with respect to, so call it g of y. All right? So what is the function that represents our vector field? Well, there's a bunch of our function. There's a majority of it. Okay? There's a majority of it. Okay, what do we want to do now? Well, we still need to incorporate the other equation, right? So let's take this answer we got. Let's take this partial. We're just going to take this partial with respect to y. Okay, take the partial with respect to y. So 0, 2 x squared y, and g, partial g with respect to y. Take the partial with respect to y. Take the partial with respect to y this term. Take the partial with respect to y. You're taking the partial with respect to y. All right, and then what are we going to do? We're going to make a substitution for the partial with respect to y. We're going to take the partial with respect to y, that left-hand side, and you're going to replace it with 2x squared y. All right. They cancel. Subtract that from both sides and you get 0. So subtract that from both sides and you get 0. Okay. And what do we want to do with this? We want to integrate this now with respect to y. Okay, so see, to get the function, you got to integrate with respect to x. Gives you your building blocks here, get you started. Okay, and then you're going to have to integrate with respect to y. You got to do each separate because you can't integrate. All right, integrate with respect to y. So yeah, 0 times y plus a constant. C or k for your constant. Integrate the partial of g with respect to y, and you get back to g of y. All right, so this is the expression. So so what is our function? I circled in blue. This is where our function is. Okay, we're going to just put in for g of y comes out. We're going to put k. All right. So what do we have for our function? We have our function in terms of x and y is 3x. It's circled up there plus x squared y squared plus 0y plus k. So we're here. All right. So this is our function, right? This is our function. We're not done here yet, though. So the other problems, that was your answer, but so this is the function. All right. This is part A. All right. So here's your answer to part A. Part A wants you to find the function. All right. That's part A. All right. Part B wants you to evaluate along the curve. Okay, so evaluate along the curve. So how do you evaluate along the curve? You're going to do the f of b minus f of a. All right, so for part B, you're going to take f of b minus f of a. Right? And just plug it in with that function. Okay? And you can drop the k because it's going to subtract out anyways. Do you remember with, like if you have an indefinite integral, you need to have a plus c for a constant of integration. But if you have a definite integral, we don't put the plus c, we just evaluate it, right? So they want you to evaluate it. So you're going to plug in 4 for x, 1/4 for y. So you're going to have 3 times 4 plus 4 squared, 1/4 squared. Okay, we don't need the plus k. Plug in the lower bound, you get 3 times 1 minus 1 squared times 1 squared. Okay, so you have 12 plus 1 minus 3 plus 1. So
minus 1 plus, I'm sorry, you wrote on the bracket on the right, 3 times 1 minus, yeah.
Got it. Thank you so much. Thank you. Okay, so distribute the negative. So the answer is 9. Yeah, that's That's how it works. So, and I still have 2 more examples. You know, we need to do them. We need to do at least one of them because one of them's got an X, Y, and Z. So I need to show you how the X, Y, and Z works. But this is the idea. It takes some practice, right? We're pretty much finishing up the course tonight too. So keep that in mind because you just need to practice these problems at the end of the chapter and make sure you're comfortable with it. Fundamental theorem. Plug in the upper bound, plug in the lower bound. Okay, this is how I'd handle it with multivariate. Except for you actually have to take a vector field, write it as a function so we can work with a function. Not all vector fields can be written as functions. All right, got another one for you coming. Ready?
Also, real quick, because you wrote it's f of b minus f of a. It's always going to be like in the problem how it's listed from 1/1 to 1/4. Sorry, it's always going to be from A to B there, right? So then when we're doing part B, like because it's not like specifically labeled A and B, I just didn't know if like the order mattered.
Because it says I copied it like this, like verbatim out of the book. Because it says from there to there, you could assume that because usually when you set up a single integral, it's like from A to B.
Right.
Lower bound B is the upper bound. So because it says from 1/1 to 4/1/4, then 1/1 is your A-ish.
Okay, so assume that it's from A to B always listed in.
It is that.
Got it. Thank you.
Yeah, they'll give it to you that way. Good. So anything else or anything clarification or just making sure you see it? Okay, what if you have X's and Y's and Z's? Well, if you have X's and Y's and Z's, watch how this is going to go. All right, so X's and Y's and Z's. Why doesn't my page want to turn? All right, so there we go. Number 15 and number 16. I have 15 and 16 because you can see that the curve down here is very different, and I couldn't find even numbered problems that had this going on. So I thought we would do 15 and 16. Okay, so first of all, you can't check conservative if you wanted to. You haven't learned how to do that yet, okay? How do you check with 3 variables if it's conservative? You have to compute the curl. And the curl, I need to show you how to do that. I'll show you Monday at the beginning of class, okay? Not hard to compute the curl, but when you compute the curl for a 3 for an X, Y, Z, that's how you're going to figure out if it's conservative, okay? So for right now in this section, they just have to tell you, hey, this is conservative, okay? Which means that this is your partial with respect to X, partial with respect to Y, partial with respect to Z. And we have to write this vector field as a function, okay? How do you do it when there's 3 variables? The other examples we had only had 2 variables, okay? So how do we do with 3 variables, okay? And then A and B are the same. We're going to use A and then going from here to here. So we're going to do f of B minus f of A once we get the function, but we have to get the function. Okay, all right, so how do we get the function? Well, let's start with this. Our partial with respect to x, I got to make this small, so good luck to getting this fitting on the page, right, is going to be y times z. Our partial with respect to y is x times z. And our partial with respect to z is xy plus 2z. Yeah. All right, so we have that. Because this is a conservative function, this is your partial with respect to x, and this is partial with respect to y. This is partial with respect to z. Okay, so that's what that means, right? Okay, so if it's conservative, that means that your vector field is made up of the gradient, the partials, okay? So which means if we know the partial derivatives, we can integrate them to get the function. So we're going to integrate them, and there's 3 things to integrate. We've got to integrate all 3 of them, one at a time, 1 variable at a time, okay? Ready? So you want to just start with the x, okay? So to get the function, we're going to integrate We'll start with a partial with respect to x. We're going to integrate the partial with respect to x. Okay? So to get the function, let's integrate yz with respect to x. Okay? So we integrate with respect to x. To get the function, you're going to get x, y, z plus. Okay, the other problems we had to put g of y here, but this one's going to be different. Okay? Because how many variables do I have left over? I have y and z left over, not just y. So I'm not going to just put g of y. I have to put g of y, comma, z, because I still have 2 variables left over. All right? You follow? So far, got my functions right here. There's my function, okay? All right? But I still have to incorporate, I still have to do the 2 more integrations. I have to do the dy and dz integrations, right? So what do we do next? Well, okay, let's take this function that I circled. So far my answer is x, y, z plus, and I'm going to have stuff there. I got to figure out what other stuff goes there, okay? So let me take I'm going to take this, I got the y next, right? Okay, so I'm going to take the partial of this with respect to y. So what is the partial with respect to y here? It's x times z. Plus, what is the partial of this term with respect to y? It's going to be the partial of g, yz, it's just the partial with respect to y. So I'm taking the partial with respect to y, partial with respect to y, partial with respect to y, okay? Then what? Then I'm doing the partial with respect to y, right? Make your substitution, okay? So make your substitution for the y, all right? So my partial with respect to y is x times z substituted in, okay? So you substitute xz equals xz plus partial with respect to y. The xz's cancel, don't they? So 0. All right, then what do? We're going to integrate with respect to y. Okay, so we're going to integrate with respect to y. So integrate with respect to y. Integrate both sides with respect to y. Okay, integrate the left. You get 0. Integrate the left, you get 0 plus not a constant. Not a constant yet. Why not? We've still got the z left over, all right? So what do you want to call it? H of z? That's what your book calls it, okay? Integrate the right side, all right, integrate the right side with respect to y, g of yz. Okay, so you're here, all right? Are you following this step? So I want to change something right there. I'm just going to put 0 times y. You don't have to do that, okay? So we're here, okay? So now, so let me substitute this into my function here, okay? So now what's my function? Okay, let me update. I'm going to update my function. So my function now up here, I'm just updating it, is xyz plus my g of yz. Now my g of yz, because I did the second round of integration, is h of z. Okay, so now here's my updated function because I took care of the y's, right? Now what do I have to do? Well, now next we need to do the z component. Okay, so we're going to take the partial of this answer with respect to z. Take the partial with respect to z. What is the partial with respect to z? It's xy plus the partial of h with respect to z. All right. And what do I do with this? I'm going to make my substitution, okay? All right, my partial with respect to z is xy plus 2z. That goes in here. So I'm going to put xy plus 2z. That goes in the left side, all right? And the right side, I have xy plus partial of z with respect to z. That's what I have, okay? The xy's cancel. So you have 2z on the left, right, equals partial of h with respect to z on the right. So far, so good? Now what? Integrate both sides. Integrate both sides with respect to z. So to get the function, we had to integrate the x, simplify it, integrate the y, simplify it, get the z. All right, so let's go ahead and do the integration. Integrate 2z with respect to z, z squared, plus your constant of integration, right? All right, equals h of z. So what do we want to do now? We want to, let's update our function. Let's update our answer there. So what is our final function going to be? It's going to be x, y, z plus, what is h of z? Z squared plus k. All right, so here's your final function. It's f of x, y, z. Okay, so that's going to equal x, y, z plus h of z, which is z squared plus your constant of integration. Here is the function that represents that, this is the function that represents that vector field. All right, that's part A. That's all part A. Okay, so this is all part A. Part B, make sure you get your vector field right. Part B just wants you to evaluate it. Okay, so it wants us to evaluate from so you're just going to plug this point into your vector field, right? Okay, so we're going to take f of 4, 6, 3 and subtract from that f of 1, 0, negative 2. Okay, that's how it works for multivariate. So I'm gonna try to make this fit on this page, right? So we have 4 times 6 times 3 minus 3 squared. And we're subtracting from that 1 times 0 times negative 2 and subtracting from that negative 2 squared. So over here we have thinking 24 times 3 is 24 times 3, so it's 72. Oh, it's plus. I know it's plus. Sorry, it's plus. There's a plus sign there. That's plus. Did I make a mess? Ugh. All right, so we have okay, so 72 plus 9 is 81 minus 4. So the answer is 77. This is number 15 in the book. So the back of the book answer should say it's 77. All right, so that should be the back of the book answer. So there's part A, there's your function. There's all the steps. That's your function. And then there's part B. Okay? That's how you handle it with 3 variables. So we are going to start Green's theorem now. Okay? I know I had 5 examples here in case we had time. We did 4, which should be good. All right, we should be good. That 5th example, I'll make it part of the review on Monday. Okay, so I'll just take the examples we didn't get to on this and that whatever over the last couple of classes, and I'll just put them together and we'll do a nice little review. Okay? All right, so that finishes 16.3, and let's go on to Green's theorem and do a couple of those. And if we don't get to all of those examples, I'll incorporate that, and I'll just build all the examples we didn't get to will be our review. Do you have any questions, or I'm just looking at the chat bar over here. So we're gonna move. All right. So is the page going to change for you? All right. We're not doing this one now. We'll do this one. We'll do this one on Monday as part of our review. I want to get to Green's theorem. So what I circled heavily in red here is really what you need to know. Okay? What does Green's theorem do? It takes a line integral and it changes it to a double integral. So you can just do the double integral instead of having to parameterize, instead of doing all that, it's Green's theorem. He's the guy that came up with it. He figured out a way to take now remember, line integrals are relatively new anyways, right? I mean, it's relatively it's the last couple hundred years. So he figured out how to take a line integral and write it as a double integral. Okay, so you have an integral in terms of x's and y's. Well, hey, why not just leave it in terms of x's and y's and do a double? Change it to a double. Okay. Now here's the catch. All right, all the writing up here is like your hypothesis, right? So your C, which is the curve, right? That's the curve you're traveling along. So the C has to be positively oriented. Has to be. So when you travel, they're going to tell you the path it's traveling has to be counterclockwise. If it's counterclockwise, you're good. Okay. If it's clockwise, you got to put a negative out front. All right. So we want it to be counterclockwise. They're going to give us, so they're going to tell us what the integrand is, right? And they're going to give us the curve. They have to. We want to travel the curve, and if it's counterclockwise, we're good to just go ahead and make the substitutions. But if it's clockwise, you got to put a negative out front to change the orientation. Piecewise, smooth, simple, closed curve. P and Q have continuous partial derivatives. These are all the details in the hypothesis. Then this is how we change it. Okay, you're going to take the partial. Where'd my iPad go here? Should be good. Okay, so it's going to be set up like this. Okay, and you're going to take the partial of Q with respect to X over here, and you subtract the partial of Q with respect to Y. You just got to remember that that's how you set it up. dA. And you'll have options here to do in rectangular. You're going to have options here to convert to polar. Okay. Examples that we're going to do are number 6, 10, 12, and 14. Okay. And I think there's slim to no chance that we're doing all 4 of those tonight, but we should get through a couple of them. All right. And when we don't get through, we're going to just, this is the end of the course, really. Okay. On your calendar, it says curl, and it says divergence, and it says Stokes' theorem. That's like, for Valencia and for the standards, that's beyond the scope of the course. The other calculus teachers don't really teach that. All right. So if we have time, I'm going to introduce that anyways. When I took Calc 3, my professor taught all that to me. Okay. So, I mean, even with the little tiny college I went to up in New York. So, but this is, most of your Calc 3 courses, they end the course with Green's theorem. All right, so this is it. So we're going to change a line integral to a double integral. All right, I always like to try to take these big, huge ideas and put them in 10 words or less. We're taking a line integral, we're going to change it to a double integral. Green's theorem tells us how to do it. The proof is in your book. You should give that a read, okay? Especially if you're going to take a lot of math, you should dig into some of the theory. You should figure out why these work, okay? So, I mean, I wish we had more time so we can actually go over all that stuff. I mean, but I think I spend more of my time doing examples, though. Ready for examples? Speaking of examples, we're going to get started. So, all right, so we'll go ahead and get started. All right, let me Okay, so the idea is to do 6, 10, 12, and 14. So number 6 and number 10 are already positively oriented. So you don't have to worry about changing the sign. By the way, when they put some of the, when I don't have it here, but when they put a little circle, if they put a circle around here, that means it's positively oriented. Okay, so it means that. So if you have that symbol, they didn't put the symbol on these because they're telling you the directions. It's already positively oriented. So we want to do 6 and 10. All right. And then number 12 and 14 are just like 6 and 10, except for you got to check the orientation first. You got to make sure that so if you're going counterclockwise, you're good. But if you're going clockwise, you got to put a negative out in front when you set up your double integral. All right. So do we need 4 examples? We really just need 1 or 2. We don't need 4. But I mean, whatever we don't do today, all these examples that I have blank pages of, I'm going to use that to put together our review. All right. So for the final exam and for your test. So let's do the first example, which is number 6. And I wrote the directions here. Use Green's theorem to evaluate the line integral. Right along the curve is positively oriented. Okay. So we're going to use Green's theorem. We're going to evaluate it. What's Green's theorem again? It's written over there on the other page, isn't it? Okay. So we have a positively oriented curve, and we're going to change it to a double integral. Okay. So, and how do we do that? Well, your new integrand, you're going to take the q with respect to x, and you're going to subtract the partial of the p with respect to y. Okay, so this is just I'm not going to keep writing that down, but that's what you do. It's very formula driven. It's just, you're just plugging into a formula. Okay, so let's go ahead and do that. So you can see it up here. Okay, so let's go ahead and change. So the double integral, let's take care of the integrand first. Okay, so we want the partial of q over here with respect to x. What is it? It's 2x. You're going to subtract from that the partial of the p component over here with respect to y, which is 2y. So there's your integrand. Okay. What about the base? Yeah, we got to graph that. It's a triangle, so the vertices are the origin. 2, 1, so to the right 2 and up 1. And 1, 0. I mean 0, 1 is here. Okay? So this is your base right here. It's here. That's it right there. Okay? So we need the bounds, so let's write some equations. This up here is y equals 1. All right, this down here is y equals, the y-intercept is the origin. What's the slope? It's going to be 1 minus 0 over 2 minus 0. 1 half x. That's not hard to get, right? 1 half x. Okay, check that. All right, and so I'm thinking, just because of the way I labeled this, I'm thinking like a type 1. Okay. So dy dx instead of dx dy. What are the inside bounds? The inside bounds are going to be from here to here, right? From here to here. So the inside bounds are going to be from 1 half x to 1. What are the outside bounds going to be? They're going to be from 0 to 2, right? So 0 to 2. So you're setting up a double integral just like we did at the beginning of chapter 15. You got to set it up. You got to use the base to set it up. Green's theorem just helps us with the integrand. Okay, and he proved that this will work. He proved that you can take a line integral and do this to change it to a double. And then you evaluate it. So let's integrate with respect to y first. Okay, so 0 to 2, 2xy minus y squared. Okay. So, all right, you okay with the setup? Very formula driven, right? The integrand is using Green's theorem as the formula. All the rest of it is exactly what we did. We've had quizzes on it and everything, so I can make sure that you kind of studied it. All right, and then evaluate. So when you plug in the upper bound 1, okay, so we still have to do the 0 to 2 when we're done. Plug in the upper bound 1, and you get 2x minus 1. Plug in the lower bound. When you plug in 1/2 x for y, you're going to get x squared minus, and you're plugging in 1/2 x for y, so this is going to be x squared over 4. And now let's just go ahead and integrate with respect to x. Okay, so integrate with respect to x. All right, or do I want to combine this? Let me combine this. Okay, so 0 to 2, so you have what? 2x minus 1 minus 3/4 x squared. Yeah. Okay, so let's integrate this. You're going to integrate this, you get x squared minus x cubed over 4. Right? 3x to the third over 3 times 4. The 3's cancel from 0 to 2. Plug in the upper bound, so 4 minus 2 minus 8/4. Plug in the lower bound and you get 0 minus 0 minus 0. Well, that was 0. So, in case you were wondering if that can happen, I guess that answers yes. So that came up. So, all right. And if it's okay, let's do another example because we still have 15 minutes, so we can get another example in. So, really, do you get the setup? Green's theorem takes care of the integrand, and then in terms of the bounds, we do what we did before. We do what we did back in chapter 15. Green's theorem takes a line integral, single integral, and changes it to a double, so we can just evaluate a double integral the old-fashioned way, which is what we did in chapter 15. So, yeah. Let's do, what did I say what was next? Number 10, 10, 12, and 14, but let's do number 10. All right. I don't know how to copy a segment of that. See, Green's theorem, you got Green's theorem down. I don't have to write that down on the next page, right? So let's do number 10. Turn the page. There we go. Okay, there's number 10. So we're going to take Green's theorem. Let's take care of the integrand first. So you're going to take the partial of q, they call that q, right? Partial of this piece over here, the q piece with respect to x. So that's going to give you 3x squared. Minus, take the partial over here with respect to y. That's going to give me a negative 3y squared. All right. What am I doing with the base? I have circles. X squared plus y squared equals 4 has a radius of 2. X squared plus y squared equals 9 has a radius of 3. So my base is going to be right in here. Okay, so what are you thinking? I'm thinking polar myself. Yeah, polar. So polar means over here dA is going to be r dr d theta. Your inside bounds are going to be the radius bounds, and the radii go from 2 to 3. Your outside bounds, well, it's the whole thing, so you're going all the way around. All right, set it up. We like polar. Polar is usually easier to set up. Okay, we like when you get to Calc 3, we like polar. All right, so you can factor out the 3 there. So you have 3 times the quantity x squared plus y squared minus a negative, right? All right, r dr d theta. Okay, so I need to finish my conversions in here. So what is x squared plus y squared? It's r squared, isn't it? Okay. All right, do you have questions with setting it up? Green's theorem, the integrand is a formula. It's what it is. It's really cool. Read the proof. Check out why it works. All right. I'm more fascinated than anything about what goes on in these mathematicians' minds. Come up with all this stuff. All right. I mean, if you can set it up, you can probably get the rest of the way through it. Let's finish it off. Okay. So we're going to integrate. What am I integrating here? I'm integrating 3r cubed. So I'm going to get 3r to the 4th over 4. That's going from 2 to 3. Okay, so we want to evaluate that. So plug in the upper bound. So 3 to the 4th is 81. 81 times 3 is 243. 2 to the 4th, 2, 4, 8. 16 times 3 is 48. So it's 48. Okay. So 243 minus 48, what's that, 195? Okay. So when I integrate this, what do I have here? So I'm going to integrate from 0 to 2 pi. It's 195 fourths. All right, so integrate that number with respect to theta, you get 195 fourths times theta. Okay, and then this gets evaluated from 0 to 2 pi. So plug in the upper bound, gives you 195 halves pi. Plug in the lower bound, you get 0. So your answer is right there. Okay, so Green's theorem, and it's easy. Green's theorem's easy. Changing a line integral to a double integral. The integrand, you just use the formula. All right, the bounds, you just have to do what we did back in chapter 15. Okay, and that's how Green's theorem works. Okay. 721. I think we have time to do one more example. I don't know how you guys are feeling, but it's a lot of stuff tonight, I know. All right, but we're kind of finished it. We just pretty much finished the content of the course that we're required to finish. We finished. Okay, we got it all in this modality and all that. We got it all in, but we finished the course. All right, this is the content that you have to do. All right. I do want to talk curl and Stokes theorem. Just that stuff is how you would handle the conservative with 3 variables. All right, and I think you use it. I think some of your science classes use it. So I want you to at least have been exposed to it. It won't be tested or anything, but all right. So let's take a look at the third example. 8 minutes left. So let's see if we can kind of do the third example. At least get it started. If we can get it started and set up, I might not have time to get through it, right? Okay, but you know how to, once you change it to a double integral, you know what to do. We've been doing that for quite a while. All right, so but let's set this one up. Okay, now this one is using Green's theorem, right? So we're doing the same thing again. We're using Green's theorem. We're going to set it up, but we got to check the orientation on this, right? Because remember that with Green's theorem, it's got to be positively oriented. Okay, and if it's not positively oriented, you've got to put a negative out front. Okay, so let's just see how that works with this example. So Green's theorem. All right, so we're going to use Green's theorem. And they gave us this, right? So what is our integrand going to be? So when you have the vector function, here, let me go back to the formulas, because I wrote it down on the formula page. All right. So when you have this vector function, this vector field, this is what we're dealing with. It's the same. This converts to this, converts to that. Okay. So your x component and your y component are the x and the y in the vector field, right? So, all right, so here's how this works. So and we have to check orientation. So you're going to take, we'll set it up in bold here. You're going to take this partial with respect to x over here is 2x minus partial over here with respect to y is 2y. There's your integrand. Okay. Then your base, well, let's see what we got going on. So we can figure out how to set up the bounds. Okay. dy, dx, dx, dy. Let's set it up. So C, this is the y-axis, this is the x-axis, and I'm going to read this down here, and I'm going to, all right, so C is the arc of the curve y equals cosine from negative pi over 2 to pi over 2. So this is here. That's the cosine. This is negative pi over 2, 0. Okay. To pi over 2, 0. Okay, so what are they telling me here? They're telling me I'm going from this point to that point. Okay, so they're telling me I'm going this way. Okay, all right. And then they're telling me, so I'm going from negative pi over 2, 0 to pi over 2, 0, that direction. And then I'm going along the line segment from pi over 2, 0 to negative pi over 2, 0. So they're telling me this. Okay, now which way am I traveling here? This is definitely clockwise, right? Right, this is negatively oriented. All right, we don't want it negatively oriented. We want it positive orientation. Okay, so we want positive. So what do we have to do? See, this is clockwise. All right, we want the orientation to be counterclockwise. So if the orientation is not counterclockwise, then we need to put a negative out front. The negative out front is to change that orientation. Are we okay so far? Now we got to set up the bounds. Okay, well, that's not bad to set up the bounds. You want to go this way and do a type 1 again? Let's go this way and do a type 1. Okay, so go that way and do type 1. So what are my inside bounds going to be? They're going to be 0 to the cosine curve. Do you see it? The inside bounds are going to be 0 to the cosine curve.
I'm sorry, could you explain again how you know it's negatively oriented?
So positive orientation is defined as counterclockwise. It's in the theorem. So C has to be positively oriented. To use this formula, C has to be positively oriented, which they define in the reading that's counterclockwise. All right. So, and if it's not counterclockwise, you got to put a negative to change the direction. Okay. So your curve needs to be positively oriented when you use the theorem. It needs to be going counterclockwise. Okay. So number 1 and number 2, we didn't have to check orientation because they told us it was positively oriented. When you get to this section, they're not telling you it's positively oriented, so you got to check it. And they're describing here exactly what you're doing. They're saying you're going from here, that way along the curve to here, and back to here. So this is clockwise. That's negatively oriented because it's clockwise. We want it to be counterclockwise. How do you change clockwise direction and change it to counterclockwise? You're going to change the sign, put a negative out front. Okay? That's a negative sign. Do you get that's a negative sign? Did I supersize it and make it look too weird? All right, that's a negative. We got to put a negative out front. Okay? Because we have to change this orientation. All right? So, and then the inside bounds, because we're doing type 1. And what are the outside bounds? The outside bounds goes here all the way over to here, right? Negative pi over 2 to pi over 2. Can you see it? All right. And then that's the setup. And you would do this in rectangular. And this is going to be busy to integrate because eventually, you know, it's not hard to integrate with respect to y, but when you do the x's, it's going to involve integration by parts. Okay? And we can pick up with this one next time. I can include this on the review examples, right? So, and we can start with this so we can talk about the orientation and all that. All right? That was a lot tonight, but we finished the required portion of the course. Okay, everything that we're required to be able to get through, we finished. And we got through all of it. I was worried about, you know, with this real-time virtual, it's easier for me to cover stuff in class, but with the real-time virtual, I was worried. I've made YouTube videos on all these topics, okay, so if they might help. And I did different examples in the videos that I'm doing here. So I'm just kind of talking through it and explaining through it again. All right. But that's it. All right. I'm going to kind of go back through the last couple weeks' notes, and I'm going to look through all these examples that we didn't get to, and I'm going to kind of compile them and use them towards our review for the test and our review for the finals, so we have fresh new problems to do. All right. And we'll just keep practicing. So a big chunk of next Monday is just going to be review for the test. We're going to go back over and just review a bunch of stuff, okay? And then Monday the 30th is your test after Thanksgiving, and then we'll do a big review for the final exam. Okay? It's almost over. Okay? You guys are doing well, so thank you for that, okay? And it's 7:30, so have a nice weekend, all right? And in a holiday week, so enjoy your weekend. All right, let me know if you have any questions or if there's anything you need. I'll be around. I'll be around if you need anything. Okay. All right, I'm gonna stop the screen share and say goodbye to whoever didn't check out already. So, all right, enjoy your week. I'll see you Monday.